Space Nuts is taking a bit of a break at the moment. Fred and I will be back in the not too distant future with fresh episodes. In the meantime, enjoy some of the key episodes that we have presented over the years, major events in astronomy and space science. And we'll see you real soon.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on this edition of the Space Nuts podcast. And my name's Andrew Dunkley, your host, and with me for episode 193 is astronomer in charge, Professor Fred Watson. Hello, Fred.
Hello, Andrew. I did used to be the astronomer in charge. That was my
I thought I said astronomer at large.
Well, it's quite all right. No, it's
Freudian slip.
It's very, and of course, that's why I became the astronomer at large, because you only had to change 4 letters on the office door to make it come down to you.
Yes. The organ, and that sort of harps on something we talked about a while ago, where your organisation has changed names about 2 or 3 times, but didn't change the lettering, so didn't change the logo.
Exactly, same logo since 1991.
I think that's amazing. Dear. Very good. Now, Fred, have you got enough toilet paper at your place is my big question.
Well, it's very kind of you to ask. We haven't yet started tearing pages out the Astrophysical Journal to use in the bathroom.
Did you hear about the Northern Territory News, the newspaper in Darwin? They published an edition last week with several blank pages for people. This whole thing is just insanity at the highest level. There's so many people panicking over nothing. It's beyond a joke.
You might want to explain the toilet paper issue, though, to us.
I think most people are aware, but if you're not aware, I don't know where you've been, but there's been a panic buy-up of toilet paper in Australia, and all the supermarket shelves are empty. Every supermarket where I live has got no toilet paper because people have been panic buying because the Prime Minister said, stock up because you might have to be isolated for a couple of weeks because of the coronavirus. And everyone's freaking out about it. Well, not everyone. I mean, we don't care, but a lot of people are freaking out about it. But I'm going to bring some astronomy into this, Fred.
Oh, good. I wondered where it was going.
I think this is the 2020 version of a caveman seeing an eclipse and thinking the world's going to end.
Oh, probably.
That's what this is.
Yeah.
So I think people need to take a long, hard look at themselves and give themselves an uppercut, to use an Australian term, and just get on with it. This is ridiculous. Totally ridiculous.
The good news is that those particular people will, they'll never need to go and buy another toilet roll again.
Not for eternity. They'll get buried with this stuff.
Yeah, that's right.
I'm suggesting that if they're going to, panic buy toilet paper, get some baked beans and some long life milk so that when you eat it, it'll taste a bit better. Now, let's get down to business. Today on Space Nuts, we're going to look at something that scientists have discovered for the first time, and that is that space-time is dragging. Not everywhere, but they've found that it is dragging in one particular place, which sounds unusual. And what does dragging actually mean? We're also going to look at a couple of clever students in terms of a name for the next Martian rover. This follows on from Sojourner, which I think is a great name, Spirit, Opportunity, Curiosity. So what are they calling the next one? We will tell you. And a 17-year-old intern at NASA, day 3 on the job, has found a planet 6 times or nearly 7 times larger than Earth. I mean, how lucky is that? Those are some of the things we'll look at today on Space Nuts with Fred Watson. Let's start off, Fred, with the fact that space-time is dragging. What is it dragging and why?
It's a phenomenon to do with the theory of general relativity, or rather the general theory of relativity, which of course was produced by Albert Einstein in 1915. Not long after that, I think about 3 years later, let me just step back a minute. That theory, of course, says that as soon as you put matter into space-time, and space-time's really just space, but with a fancy name. As soon as you put matter into it, because of course time's part of it as well, as soon as you put matter into space-time, it is distorted. And that distortion is what we feel as gravity. And that in itself is pretty hard to get your head around. Space-time bends because matter's there. But it was about, I think, 3 years later that two Austrian scientists by the name of Josef Lenzer and Hans Thierring, they worked out that you would get a phenomenon if you have a massive object rotating. You get a phenomenon which is almost a swirling of the space-time around the object. It's called frame dragging. And so as the Earth does it, as the Earth turns, it's not only distorting the space that's holding us on with the force of gravity, but to a much lesser degree, it's also dragging the surrounding space-time with it. Now, no, you're looking baffled, Andrew.
It's just a lack of sleep because I'm worried about where I'm going to get a roll of toilet paper.
Well, just watch out. Don't drag your space-time with it when you find it. We usually anglicize Josef and Hans's names to the Lenz-Thierring precession or Lenz-Thierring effect.
Okay.
That's how most people speak of it, even though they wouldn't have called themselves that. Okay, it has been tested, this theory. It was, as I said, I think it was 1918 when it was produced. But the first test of it was done in the early 2000s. A spacecraft called Gravity Probe B was launched into orbit around the Earth by NASA in collaboration, I think, with Stanford University, which carried on board very, very sensitive gyroscopes. And by using those, the physicists running the experiment could detect the frame dragging of the Earth itself. So it's all about subtle motions in the satellite. And that tells you that, yes, you have proved, because there's nothing else that would give rise to those subtle motions, you've proved that frame dragging is true. But it's only been detected around the Earth. So now cut to the chase, because for the first time, it has now been detected in an astronomical object. And this is a really nice story because it pulls together the fundamental physics of frame dragging with some of the big adventures that here in Australia we are taking part in, particularly in terms of radio astronomy. The story goes back 20 years, actually, Andrew, to the Parkes Radio Observatory in New South Wales, the very same state that we are both in at the moment.
I'm just a 1 hour drive from that telescope.
Yeah, that's right. You are indeed. Exactly. It's just down the road for you.
Yeah.
Very, very well-known telescope, the Big Dish, it's usually called.
And very distracting when you're driving along the highway because you just want to look at it. But
you can't stop looking at it, I know.
Can't help yourself.
I don't have that problem because usually when I go down there, that's where I'm going.
Yeah.
So I just watch it getting bigger as you get nearer to it. 20 years ago, the Parkes Radio Telescope discovered a white dwarf pulsar binary system. I'll tell you its name and then we can get that out of the way. It is, actually, I've got to magnify the screen so I can read it.
You're showing your age now, friend. You're showing your age.
PSR J1141 -6545. There you are. Put that in your diary. That's
it already.
As have I. It is a white dwarf pulsar binary system. What does that mean? It means you've got a white dwarf star, which is an object the size of the Earth, but with the mass of a star in it, made of electrons all crushed together, or the electrons are the only thing that hold the thing, that start the thing from collapsing. So that is a massive object. Around it is this pulsar, which is another massive object, a neutron star. The two are in mutual orbits, and so the telescope discovered that phenomenon, the binary system. So the pulsar itself is beaming out radiation from its poles. Pulsars, as you know, because you and I have spoken about this before, effectively are extremely accurate clocks. They basically blip out radio radiation as they rotate. That's what the Parkes dish detected. And the precision with which they do that is better than atomic clocks. They are so regular. Just as one smaller piece of information in this, the pulsar itself orbits the white dwarf every 4.8 hours. So it's a system. It's whizzing round. That's right. Now, what has happened over the last 20 years is that astronomers have been able to use this timing phenomenon, the regular timing of the pulsar, to measure the pulsar's position in respect to the white dwarf, because essentially accurate time means accurate distance in terms of measuring, where the pulsar is. And it's that measured over 20 years that has demonstrated that this frame dragging phenomenon is taking place out there at PSR, whatever it was, J1141 minus 6545. So what the scientists, and there's a group of scientists from many different institutions, including institutions in Germany, the Square Kilometre Array Organization, that is the headquarters of this great new telescope that we're planning, the Square Kilometre Array in Western Australia and in South Africa. The headquarters are in Manchester, or near Manchester, at the Jodrell Bank Radio Observatory. One of the scientists involved with this work comes from that organisation. So that means he is relatively closely connected with Australia, because Australia is one of the host nations. And I should just mention that the Parkes dish, plus another telescope called the Molonglo Observatory Synthesis Telescope, again here in Australia, which has been involved with this work. They are both pathfinder telescopes for the Square Kilometre Array, so very important in this large scale project that is currently under construction, or soon will be under construction. That's getting in the plug for SKA, but the research itself, as I said, involves scientists from Germany, Australia, New Zealand, and actually Denmark too. And what they've done is they've looked at the way these pulsar signals have changed over the 20 years, and they find a change in the pulsar's orbit, which amounts to 150 kilometers. And we're now talking about something that's 10,000 light years away, Andrew. So being able to measure a change in orbit of 150 kilometers at that distance is an astonishing accomplishment. But it turns out that change is exactly what you would expect from frame dragging by the white dwarf itself. And that's the only thing that can account for it. So it is the first time that we've demonstrated this swirling of space actually beyond the Earth's vicinity. And it's an important, a really important result, which is rightly being celebrated all over the science media. Astronomers detect distant space-time dragging for the first time.
So I guess the point of this is the massive, or the mass of this event, rather than, you were talking about how Earth does it, but we're talking about something on a much larger scale.
That's right. Yes. Well, the white dwarf itself, whilst it's probably not much bigger than the Earth, its mass is much larger. Yeah. You're talking about, you are talking about something happening on a larger scale. I confess that I am not an expert on the lens searing effect, but it is very interesting stuff. And when you read up about it, it's quite inspiring that, all those years ago, these guys worked out that space-time is being dragged around by the Earth.
And if you, like me, and you don't want to read anything about it, there's a fabulous animation on the skatelescope.org website where you can see in about 1 minute and 20 seconds what they've learned over 20 years. It shows you how the effect works. It's very, very good.
I might give a call out to the person who put that animation together, Mark Myers, who's at Swinburne University, because I was in touch with him yesterday. I'm using one of his graphics in a newsletter that I prepare, and I asked him, if that was all right. He said he was delighted to let us use it. And I absolutely agree with you, Andrew. His animation, which is on that website, the skatelescope.org website, is terrific.
Yes, indeed. All right. You're listening to the Space Nuts podcast. Andrew Dunkley here with Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, just another shout out to our patrons who support our podcast with dollars and cents. We thank you again for doing that. If you would like to become a patron or just look into the possibility, you can go to our Patreon website, patreon.com/spacenuts. All the information's there. If you would like to contribute to the program, you can set your own limit. But it's not mandatory. We're not asking you to do it as a condition of listening to the podcast. If you want to go on listening to it as you are, that is fine too. But anybody who contributes does get the benefit of bonus content on the Patreon website. They also get the commercial-free edition of the podcast ahead of time. So something to consider anyway. Now, by the way, Fred, my new book, shameless plug coming up, is now available for pre-order as an ebook. So have a look for that on the Amazon website. So that's pretty exciting. I'm very, very pleased with how it's all turned out. Someone actually messaged me the other day and said, I've ordered it, better be good.
You've got to remind us of the title, Andrew.
It's called The Tyrannian Enigma.
That's
Tyrannian Enigma. I'm starting. First time I wrote that down and read it out, my tongue tripped over it, and I thought, no, this is too hard. But I'm getting used to it now.
Very good.
I've developed a couple of synapses in my brain that have got my mouth around the Tyrannian No, I tripped over it. But have a look for it. The official release date of the ebook and the paperback will be April 15. And a few people have asked if I could turn it into an audiobook as well. So I'll look into that. It's just so time consuming to create an audiobook.
Sure,
not so much the reading and recording of, but the editing. Oh my gosh, that's a nightmare.
You did that for
Almost Sea is Mud. Yeah. Which was a World War I story about my grandfather in the Great War. But that started as an audiobook. So I sort of flipped the egg on that. I did the audiobook and then made the paperback. But these last two I've done the other way around, or haven't done the other way around, but I'll look into it. It's got to be feasible. And that sort of becomes the question, but we'll see how the demand goes. But yeah, have a look for it. Hugh tells me he's going to put it on our bytes.com/spacenuts page. So you might be able to pre-order through there. I haven't checked. Now let's get down to a couple of things involving students, Fred. These are exciting stories. I particularly like this one, which involves the naming of the Next Mars Rover. Now we've heard of Sojourner and Spirit and Opportunity and Curiosity, some of which have gone above and beyond the call of duty. But they aren't the last rovers. There'll be future rovers, and it looks like some students have got involved in the naming of the next one.
Well, that's right. It was, I think this is what NASA does normally with its rovers. It puts out a competition to school students. And suggest names for our next rover. And of course, the next rover is what's been called until now Mars 2020. It will be launched July or August this year. I think its landing date on Mars is the 18th of February next year. So just under a year away. Until now called Mars 2020. So during the closing months of last year, NASA put out the invitation to school students. I think it was school students of all ages from kindy to year 12, and invited them to submit suggestions for the name of the rover, and they received 28,000 submissions.
I know, that's amazing.
It's not bad, is it? That was back in August, at the end of August last year, when they put the invitation out. But fortunately, it wasn't just one person who had to read all 28,000, because these were essays saying why it should be a particular name. They had 4,700 volunteer judges. They were educators, professionals in the space field, and space enthusiasts. And they eventually got down to 155 semi-finalists and then 9 finalists. And I can't remember, but I think you and I talked about this last year.
Yes.
Because there was a list of very elegant, they were all great names actually for a rover.
Robert.
And then they put that out for public voting. And in fact, it was worldwide, and there were many submissions came from Australia. They received a total of 770,000 votes.
Wow.
To chew through, to work out what the final name should be. And eventually they got one answer. And
hang on, drum roll.
It came from a youngster by the name of Alex Mather, who's at a school I've forgotten. I think he's in Virginia. I can check that in a minute. But here's the drum roll, he was the person who suggested the name Perseverance, which is the name of the new spacecraft.
Yeah. That is a fabulous name for it, because it does actually tell a story behind all the missions to Mars over the years and all the work that's gone into it. They just, all the successes and the failures and the near misses. It is perseverance that keeps it going.
That's right. This spacecraft as well could be the one that discovers life on Mars.
Yes.
Because that's what it's, what the aim is. It's unlike Curiosity, whose mission was to discover whether Mars was ever habitable, which it did within about the first fortnight of its presence on the planet. Perseverance is looking for evidence of past or present life, with many different instruments that will do that. And I suspect Perseverance might be the characteristic that it needs more than anything else. It will probably be quite a long mission. It's unlikely that, as soon as it drops down, it's going to find evidence of Martian microbes. One would expect that it might have to move around on the surface a bit, but it will do that.
Yeah, great. And only slightly pipped the number 2, which was, do I have to go to Mars?
Yeah, that's the one.
Yeah. I'm fascinated by the fact that they got 28,000 submissions for the name. It reminds me of an author, a children's author in Sri Lanka last week, who got 20,000 submissions for the ending of her latest book.
Okay.
And they came out and they're going to publish it with 1,250 endings, which is a Guinness World Record. And I think those sorts of responses really show where you stand in the world. So when I asked for a title for my book, I got 5.
Yeah, you did. Yeah. I think that's pretty good. more than the number of people who read my book. The bottom line here is congratulations to young Alexander Mather.
Yes.
He is a grade 7 student. Now I'm guessing that means he's about 13, or thereabouts. And he put together a really remarkable entry. He said some very, very, very nice comments about the competition and his entry to it. He says, this is actually in the NASA press release. He says, this was a chance to help the agency that put humans on the moon and will soon do it again. This Mars rover will help pave the way for human presence there, and I wanted to try and help in any way I could. Refusal of the challenge was not an option.
Lovely. That is
great stuff, isn't it?
Good on him. Okay, so watch out for Perseverance, which should hit the Martian surface in a little under a year. Still on students doing great things, this is a fabulous story about a 17-year-old who's doing an internship at NASA and has found a planet on day 3.
Day 3, that's right. It is. It's great stuff. This is a young man called Wolf Cookier. I hope I'm pronouncing his name correctly. He scored a 2-month internship with NASA. So during last northern summer, he was at the Goddard Space Flight Center in Greenbelt in Maryland. And what he was doing on day 3, I think he probably started off doing this, he was trawling through data from TESS. So TESS is a NASA spacecraft. It is currently operational, doing a great job. The name is an acronym for Transiting Exoplanet Survey Satellite. So it's actually looking for the dimming of the light of stars as planets pass in front of them. And unlike Kepler, which only looked at a small area of the sky to do the same job, Kepler now effectively defunct, TESS actually looks at the whole sky. So the word survey in its name is very important because it actually has a chance to look at the entire sky. So he was looking through the data. Actually, there's a nice quote again from Wolf. He says, "I was looking through the data for everything the volunteers had flagged as an eclipsing binary. That means 2 stars orbiting around their common center of mass. One passes in front of the other as seen from the Earth. And so you get what we call an eclipse. So they're well-known stars. They've been well-known for more than a century. He was looking through everything volunteers had flagged as an eclipsing binary, a system where 2 stars circle around each other and from our view eclipse each other every orbit. About 3 days into my internship, I saw a signal from a system called TOI 1338. At first, I thought it was a stellar eclipse, but the timing was wrong. It turned out to be a planet. I noticed a dip or a transit from the TOI 1338 system, and that was the first signal of the planet. First saw the initial dip and thought, oh, that looked cool. But when I looked at the full data from the telescope at that star, I and my mentor also noticed 3 different dips in the system. So great stuff and very well spotted.
And this is a big one too.
That's right. It is.
Planets, I suppose.
It's between the it's somewhere between the size of Neptune and Saturn, rather larger than Uranus, about 7 times larger than the Earth. It's in the constellation of Pictor, and it's about 1,300 light years away.
Is it a gas giant or a rocky planet?
Probably a gas giant. Yeah. The name TOI 1338. TOI is an acronym for TESS Object of Interest, and it's one that's floating around a lot these days with a number attached to it. So of course, because of the convention, that planet that Wolf has discovered is now called TOI 1338b, because the B signifies it is the first discovered planet around the star.
Excellent. All right.
Great stuff.
Yeah, good stuff involving students doing wonderful things. You're listening to Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
And a big hello to all our social media followers that contribute via our Facebook page. If you're not following us on Facebook, maybe have a look if you're a Facebook user, of course. You can also join the Space Nuts podcast group on Facebook. That's a chance for you to talk to each other and help each other out with astronomy questions. And it's going gangbusters. People are really enjoying finding each other, and the similarity in interests is rather fascinating. So I occasionally poke my head in there, but it's actually for you, the Space Nuts podcast group. So you might want to take advantage of that. And of course, YouTube, the numbers continue to grow. So if you'd like to subscribe to the Space Nuts YouTube channel, you can do that too. Now, Fred, we have a couple of questions. I didn't preview these because I forgot, but we are going to tackle a couple of questions, and then we're going to do a little bit of homework or go back to something we talked about a couple of weeks ago just to finish it off, which was the Roche limit, which actually came about as a result of a question. But our first question today comes from Andrew Mitchell. I think Andrew's been in touch with us before. Dear Fred and Andrew, all this recent talk about black holes has been fascinating, and the last instalment got me thinking. According to Einstein's equations, black holes are supposed to have supposed to be infinitely small, infinitely dense singularities at their center. If that's the case, then how do two actually merge into one black hole? Shouldn't they just keep orbiting each other, getting closer forever? Or is the fact that black holes do merge actually evidence that singularities have size, perhaps a sphere with a diameter of 1 Planck length? Your regular plugs on YouTube channel have been paying off. I just became subscriber number 993. So we're a bit overdue getting your question done, Andrew. Thanks for joining us on YouTube, though. Still loving the show. Please keep up the mind-blowing stories. Thank you, Andrew. Black holes. Gee, we don't talk about them very often. But yeah, it's an interesting question because we talk about how the black hole itself is quite small when you compare it to the event horizon or the what's going on around it. But yeah, two merging black holes, do they actually merge, and how is it so?
It's a really good question. It's the whole black hole thing is hard to get your head around.
Yep.
Whether you're a physicist or an astronomer or somebody fighting over toilet rolls in the aisle of the soup.
That involves a black hole too, doesn't it?
I'm sure it does. Yeah, they are very, very hard objects to understand. And Andrew's question is really well made. How do two black holes merge into one? I don't think there is any need for them to keep orbiting around each other if they are of infinitely small size. I do get his point that if you've got something that's infinitely small and you put something else that's infinitely small next to it, they're never gonna touch because the dimensions are infinitely small. But in fact, as Andrew says, they do merge. We have evidence of that from the gravitational wave observations that have been made over the past 2 or 3 years. And there is this phenomenon called the ring down, which is the sort of aftermath of the merging. Now, I don't know enough about black hole physics to understand specifically what the mechanism of the ring down is, but I suspect that is where the evidence comes that you actually have now merged black holes. In fact, we know the evidence is there because you wind up with a black hole whose mass is actually usually slightly less than the sum of the masses of the two black holes that have merged, and the excess has gone into creating the gravitational waves. It's mass into energy. But Andrew goes on to make an interesting point. He says, or is the fact that black holes do merge actually evidence that singularities have a size, perhaps a sphere with a diameter of 1 Planck length? Now, introducing the Planck length is a really neat way of sidestepping the idea of an infinitesimally small object, because the Planck length is defined as being the smallest distance, and it does have a proper physical definition. In fact, it's actually the distance that light travels in 1 unit of Planck time. So that raises the question, well, what's Planck time? Let me just summarize, though, and this is coming directly off Wikipedia. The Planck length can be defined, let me read it. The Planck length can be defined from 3 fundamental physical constants: the speed of light in a vacuum, the Planck constant, that's something which physicists are very familiar with, and the gravitational constant. It's the smallest distance about which current experimentally corroborated models of physics can make meaningful statements. So what it says is, and I'll go on, at such small distances, the conventional laws of macrophysics no longer apply, and even relativistic physics requires special treatment. And the bottom line is that a Planck length, below that, all bets are off.
Okay.
We really don't understand what is happening to the physics. And maybe Andrew's point is well made, that a Planck length, a black hole, is actually what you have at the center of constituting a black hole system. I need to talk to my expert friends about this, because at this level of technicality, My knowledge is not specialist, but I do know people whose knowledge is far better than mine. And next time I run into them, I'm going to ask them exactly about these questions and hopefully feed back to Space Nuts and to Andrew and his fellow listeners.
Okay, so the question remains open, Andrew. Yeah, I think we'll give you a definite maybe.
Maybe it's the answer.
Yes, all right.
Yeah.
Thanks, Andrew. Thanks for the question. Let's move on to a question from Ulf Peterson in Sweden. Yeah. Ulf, I've got some news from you, which you may or may not be aware of, but a young lady named Julia Engström, a professional golfer from Sweden, just won the New South Wales Women's Open, which we hosted here in Dubbo a couple of weeks ago.
Great.
Because our course was closed to play for members, we got to go out there and watch these young ladies go around. It was a European tour event. She won not only her share of the prize money, but a 2-year exemption on the European tour. She's 18 years old, and she swings it like a champion. I mean, she was hitting it 260 to 280 metres, wailing it past me, and she's just a slip of a kid. But remarkable player and someone to watch out for in the future if you're a golfer. Julia Engström is her name. So there you go, Ulf. A little bit of, I can feel his pride swelling now. Now, he says, hello, Andrew and Fred. What a fantastic community you've started, and it's a global one too. I've been a faithful listener of your pods now for a year and enjoy them very much. Never imagined Thursdays could be that exciting. I'd usually say something derogatory, but I'm feeling good today. Don't know if this question might be of interest to the show. Is there any chance that it's a black hole question, by the way, Fred. Is there any chance that a black hole might not exist in its inside its event horizon? After all, black holes are claimed to be singularities, i.e. infinitesimal in size. In practical terms, nothing, right? If so, could an event horizon act as a sort of a delayed postal service, never informing anyone outside what has happened? It's like Australia Post, really. No, they're great. Actually, there's another piece of news. Dubbo Post Office here in town got Post Office of the Year.
Oh, fabulous. That's great news.
About a month ago. So we're doing all right here, aren't we?
Yeah, you're doing well in Dubbo.
Back to the questions. Would physics allow matter still to be pulled into the into the horizon, even if the black hole was gone?
Great question, Ulf. And in a sense, he's right about the event horizon acting as a delayed postal service because it stops the transfer of information. We do know that black holes can evaporate, courtesy of Hawking radiation, but basically, and that involves the transfer of information. We know that, but it's very, very slow. So the event horizon does shield the black hole from the outside world, if I can put it that way. But in terms of whether the black hole itself exists, it's kind of the other way around. The only way the event horizon can exist is if there is a black hole at the center. In other words, this infinitesimally small singularity, essentially distorting space-time to the extent that you've got this shield around it, this black hole. The black hole event horizon. The event horizon in some ways is an illusion, Andrew, because it's just the point of no return. It's the thing that won't let light out. And it certainly is black. We've seen that from the event horizon image that was released last year. But without the black hole, the event horizon doesn't exist. So there has to be this singularity at the middle with all its complicated infinitesimally small Planck length dimensions that we've just been discussing. Great question, though, and thank you very much. And yes, Sweden rocks. I was there not very long ago.
And as Monty Python says, nothing can come from nothing. Can't be nothing.
Yes.
Thanks, Alf. Appreciate the question. One more thing before we finish up, Fred, and this is a little bit of an add-on from a question about the Roche limit a couple of weeks ago. We were trying to figure out the Roche limit between the Earth and the Moon. And as you explained, the Roche limit is the point where gravity will destroy one of the objects involved in the situation. So you could probably explain it better than I just did. But basically, we were trying to figure out how close the Moon could get to the Earth before it was obliterated.
Yeah, and it's,
life on Earth would probably be obliterated too.
well, that's right. It would be a tricky situation for all of us, but it's much less than I thought it would be, Andrew. It's the Roche limit for the moon is 9,492 kilometers, and I think that's from the center of the Earth. So it's actually 114 kilometers above the surface. Imagine the moon 3,000 kilometers above the surface. Whoa!
Wouldn't it look amazing?
It would look pretty amazing. That's right.
Just for a few moments until we all die, fire
Oh,
and
we'll die. Yes, that's right. Yeah.
But that's okay. We'd have plenty of toilet paper.
No, we would. We'd be all right.
Yes. So 9,000.
Yeah, 9,492 kilometers from the center of the Earth.
Close as it could get before it was destroyed by our gravity, and we would go down with the ship.
Absolutely.
Yeah, in a nutshell. All right. Now we've got that sorted out. Thank you, Fred, so much. It's always a pleasure.
It's always a pleasure talking to you too, Andrew, and we'll speak again soon, I hope.
We will indeed. And thank you for listening. Thank you for your contributions. Keep them coming. We love to hear from you, whether it's on social media or via our website where you can send us emails. We have a little contact form there so you can send us questions. And to the patrons, there'll be some bonus material coming up real soon. Other than that, thank you, and we'll see you again next time on another edition of the Space Nuts Podcast.
Space Nuts. You've been listening to the Space Nuts Podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.